This is Chapter 4, Part 1, Basic Logic Gates. In this video, we're going to learn about the basic logic gates, which are used to implement minimized Boolean expressions. So let's do it. We're going to start off with the two-input AND gate. The two-input AND gate is as shown in the truth table for inputs A and B and output C. Whenever A and B are both 0, the output is 0. Whenever A is 0 and B is 1, the output is 0. Whenever A is 1 and B is 0, the output is 0. Only when A is 1 and B is 1 is the output of 1. So this is the one case at the bottom here where when both A and B are 1, the output is 1. And this is the Boolean expression up here. And this is the symbol for the AND gate with two inputs. This is a two-input AND gate, two inputs and one output. We can have a three-input AND gate where we have three inputs A, B, and C with one output D. This is the Boolean expression for a three-input AND gate, and the output D is equal to the AND of A, B, and C. So again, the truth table says that when all inputs are 0 or there's 1 0 in any of the inputs, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, the output is going to be a 0. The only time the output is going to be a 1 is when both A, B, and C are all 1s. 1, 1, 1, and then the output D is going to be a 1, and that occurs down here. Okay? So that's a three-input AND gate. The next gate we're going to talk about is the OR gate. And the OR gate, this is a two-input OR gate, so it has two inputs, A and B, and one output C. And the output C is equal to A or B. In other words, whenever A is a 1 or B is a 1, the output is going to be a 1. Let's look at the truth table. Whenever A and B are both 0, the output is a 0. When either A or B is a 1, the output is a 1. Well, here we have B as a 1, so the output's a 1. Here we have A as a 1, so the output's a 1. And here we have both A and B are a 1, so the output's a 1. So this is the Boolean expression again, and this is a two-input OR gate. Well, if we can have a two-input OR gate, we can have a three-input OR gate. In fact, we'll show you can have a four-input OR gate, you can have a five-input OR gate, depending on the circuit implementation that you have. So for this three-input OR gate, we have three inputs, A, B, and C, and one output D. And this is the Boolean expression. The output D is equal to A or B or C. Let's look at the truth table. Whenever A, B, and C are all 0, the output is 0. On all other cases, whenever there is a 1 in A, B, or C, the output is a 1. 0, 0, 1, it's a 1. 0, 1, 0, it's a 1. 0, 1, 1, it's a 1. 1, 0, 0, it's a 1. 1, 0, 1, it's a 1. 1, 1, 0, it's a 1, and 1, 1, 1. So the only time that this output is a 0 is when both A, B, and C are all 0. Then the output is a 0. Okay, that's a three-input OR gate. Now we have another gate called a NAND gate. And a NAND stands for not. Let me write that again. Stands for not and. And you can see from the gate that it's an AND gate right here. This is the AND gate portion. And then it's got a little bubble on the output, and that little bubble says invert the output. So if it's a 1, it'll be a 0, and if it's a 0, it'll be a 1. So that's a NAND gate. So let's look at the Boolean expression. The Boolean expression is the output C is equal to A times B, or A and B, inverted. The whole output inverted, and that's what this bubble means right here. Let's look at the truth table. In the truth table, whenever A and B are both a 0, the output is 1. Whenever A is 0 and B is 1, the output is a 1. Whenever A is 1 and B is 0, the output is a 1. And the only time the output's a 0 is when both A and B are 1, and then the output is a 0. Okay? This is called a NAND gate, or a not AND. Well, if we can have a 2-input NAND gate, we can have a 3-input NAND gate. So this is what the symbol is for a 3-input NAND gate. We have 3 inputs, A, B, and C, and 1 output, D. And since there's a bubble right here, that little bubble says the output of this AND gate is inverted. So let's look at the truth table again. It's actually just the inverse of the previous one because, of the AND gate, 3-input AND gate, because we have the inverter on the output. So the 3-input NAND gate says that for all inputs 0, the output's a 1. For a 0, 0, 1, the output's a 1. 0, 1, 0, the output's a 1. 0, 1, 1, the output's a 1. 1, 0, 0, the output's a 1. 1, 0, 1, the output's a 1. 1, 1, 0, the output's a 1. The only time the output is a 0 is when both A, B, and C are 1, and then the output is a 0. So for this case, the only time you're going to have a 1 is when A is a 1, B is a 1, and C is a 1, and then the output will be 0. 1, 1, 1, 0, and that's this location in the truth table down here. Okay, let's go to the next gate. Well, we have a basic AND gate, and then we have a not AND gate, which is a NAND. So we have OR gates, and now we have NOR gates. And what does NOR gate mean? NOR gate means not OR, which means NOR. Okay, and let's look at how that operates. This is the Boolean expression C equals A or B, the output inverted. And as you can see, just like the NAND gate, you have instead of an AND gate, you have an OR gate right here, and then you have a bubble right here, a little circle, which means the output is inverted. So we have A or B, and then we have the output inverted because of that little bubble right there, and that's a NOR gate. Let's look at the truth table. When both inputs are 0, you have a 1. Okay, that's this one here. When either A or B is a 1, these two right here, the output's a 0. When they're both 1, the output's a 0. So the only time the output is a 1 is when both A and B are 0, and then the output's a 1. And that corresponds to this location right here. Okay, so that's the basic 2-input NOR gate. Well, we can have a 3-input NOR gate. In fact, we could have a 4-input NOR gate, but we're just going to talk about the 3-input NOR gate. Just like the 2-input, except that it's got 3 inputs, A, B, and C, with 1 output, D. This is the Boolean expression for this gate. The output D is equal to A plus B plus C, the output inverted. Here's the truth table. The truth table has 3 input variables, A, B, and C. The only time the output is a 1 is right here, and that's when A is a 0, B is a 0, and C is a 0, and then the output's a 1. Otherwise, for all other combinations, that are not all 0, the output is going to be a 0, as we can see right here. This is all zeros. Okay? That's a 3-input NOR gate. We have a basic inverter gate which just says the output is the inverse of the input. And that's what this is right here. The output B is equal to the inverse of A, or A naught. This is the truth table. When A is a 0, B is a 1. And when A is a 1, B is a 0. So it's just when this is a 1, this is a 0. Okay. When this is a 0, this is a 1. Okay, that's your basic inverter. Now we have two more gates we're going to talk about, and these gates we use quite a bit in arithmetic circuits and linear circuits, and we'll talk about linear circuits later on. But basically, this is called an exclusive OR gate, and what that means is that anytime A or a B is a 1, the output's a 1. Otherwise, it's a 0. So let's look at it. The truth table says that whenever both inputs are 0, the output is a 0. Whenever both inputs are 1, the output's a 0. So for 0, 0, the output's a 0. For 1, 1, the output's a 0. Okay? The only time the output's non-zero is when either B is a 1 here, or when A is a 1, but not both. So 1, 0 gives you a 1. 0, 1 gives you a 1. That's an exclusive OR gate. Okay? Well, if you can have an exclusive OR gate, you can have a not exclusive OR gate, which is an exclusive NOR gate. So the exclusive NOR says that whenever A or B are the same, either 0, 0 or 1, 1, the output's going to be 1. And that shows us this right here. A and B are both 0, the output's 1. A and B is a 1, the output's a 1. The only time the output is going to be 0 is when either A or B are 1, but not both. So if A is a 1 and B is a 0, the output is a 0. And whenever A is a 0 and B is a 1, the output's a 0. So this is just the opposite of the exclusive OR gate. It's an exclusive OR gate with an inverter. Okay, let's look at a typical circuit implementation. This is the Boolean expression right here, and this Boolean expression says that the function is equal to A bar B C plus A B B bar C plus A B C bar plus A B C. So how do we implement that? Well, we have three product terms right here. We have four product terms. And let's look at these four product terms. This product term is A bar, B, C. So A bar and B and C. So let's look how we would do that in this first gate right here. We have A, but we need to have A bar as one of the inputs. So on this one right here, the A goes to the inverter and becomes A bar. So we have A bar as an AND gate ANDed with B, ANDed with C. So this is the 3-input AND gate, and the output of this AND gate then is A bar B C. Okay, let's look at the second one. The second one is A B bar C. So for the second one we have here single A right here, and B has to be inverted because we need B bar going in right here, and then the last one is C going in right here. So this output is equal to A B bar C. Let's look at the third one, which is A, B, C bar. So we have A right here, A, and then we have B right here. That connects to the B. And then we have C inverted to make it C bar. So then we have the output as A, B, C bar. So for the final one, we have plus ABC. So here's A. Let's draw this whole thing out. So we have A, And we're going to connect to B. And then we're going to connect to C. And the output is A, B, C. Now what do we do with these three outputs? Well, it's a sum of products, so we put them into a sum gate, which is an OR gate. So this OR gate is equal to A bar BC plus ABC bar plus, AB bar C plus ABC bar plus ABC. And so that's the function right here, which is the same as this right here, as this function. Let me do that a little better here. The same as this function right here. So that's what this is right here. Okay? So that is a typical circuit implementation using 4 AND gates, 4 3-input AND gates, 1 4-input OR gate, and 3 inverters. So this is the end of part 1. In part 1, we learned what basic logic gates are, their symbols, and how they function as shown in a truth table. Again, thanks for watching.